Okay, guys, let's get started. So I just have kind of one last topic before you guys can get rid of me. I mean, I'll be back tomorrow, but for today. So we have let's see, what did we just talk? Okay, so we talked about correcting for stratification in the standard errors, doing something like inflating the standard errors using something like genomic control. As we pointed out, for our traits, we maybe don't want to do genomic control, and so the developers of LD score regression are going to have a solution for us tomorrow. So let's talk about solutions to fixing LD score regression that involve changing what the betas are that we're estimating. Okay, so the first thing that we've talked about a bunch, and perhaps the most reasonable, easy path, is we maybe just want to restrict our sample. And so, we know that there are big problems when we have individuals of different ancestry in our group. So we say, let's just have a sample of just people of European ancestry. Or let's just have a bunch of people of African ancestry or Eastern Europe, Eastern Asia, or something like that. So that's kind of a first pass that we can do, and that should solve a big chunk of our problems. It does not necessarily solve all of our problems. As evidence of that, do I have that? No, I'm going to be later. So as evidence of that, you can remember we saw those figures where our first two principal components were predictive even within Europe, which means that our SNPs are predictive even within European samples. So we should think of this as just a crude, let's get rid of the big problems, but there's still going to be some underlying stratification that we need to take away. So how are we going to do that? Well, we've been talking about this a bunch already, so let's talk about it some more. We can use principal components. Yeah. Woo! Okay, so remember that this was our model. So we had our phenotype. It's it's the sum of the SNPs, and and there's this G term here, which is affecting the mean. So if this is like chopstick use, then this G might just be differences in Asian populations, or whatever it wants to be. So if we knew G, if we knew exactly what populations there were that were causing G to vary, then we could just throw in ancestry fixed effects, and it would solve our problem. Kind of in the same way that restricting our sample would solve the problem. There's kind of two reasons that's hard. One of which is we don't always know what the person's ancestry is exactly. And then also, we think we've been talking about ancestry as if it's this categorical thing. Whereas it's better to think of it as this continuous thing, which is why just restricting to whites is maybe not quite right. And this measure of the first PC is explaining. It's not just clumping in two groups. It seems to be just spreading them out north and south. And so even in clumps, it's maybe not necessarily the right thing. But in principle, if we knew G, we could control for it. It would solve our problem there. We don't know G, and so we say, well, let's think if we can find a proxy. Is there something that's kind of G-ish, something that's going to explain the variation in G, and so it'll get rid of the bias that's being introduced because G is predicting, or a person's SNP is predicting their ancestry, which is predicting G. And so the reason that we turn to principal components is if you think about what principal components, as you know from your problem set, are trying to capture kind of the dimensions of the most variation. It's trying to tell you kind of what are the things that are able to group people in a way that maximally explains the variation in your sample. And so what's the thing what is your SNPs most informative about? And your SNPs are because you get your SNPs from your ancestors, your SNPs are most informative about your ancestry. And so a SNP seems like a reasonable place to start. So if there's variation in your principal component, that's going to be, you could think of every SNP as a noisy measure of your ancestry. And therefore a principal component's going to try to aggregate that together across all your SNPs. And like we said yesterday, this is a little bit ad hoc. I'm talking in really fuzzy terms here because it's a little bit fuzzy. I mean, there are some kind of more concrete, if you make some assumptions about how these difference in means go together, and James was telling me that you can use coalescent theory. if you want to sound fancy. But there are arguments for why these PCs should work pretty well, but ultimately we use them because they appear to work. So I just want to splash this on the screen again, because this was like the first figure I ever saw when I started doing genetics work that like totally took my breath away. So I want to explain what this is so you can be amazed. So what we've done here is we have this big European sample, and we know what country each of these people are from. And so we take the first two PCs, and PC1, we plot PC1 against PC2. And then we color code the individuals by where they're from. And so when you do this, you can see that just these first two PCs are like, when you do this, it creates a map of Europe, right? Like over here is Spain. So all the people from Spain and Portugal are in this part of PC space. And over here is like Ireland and Great Britain, and here's France. Like, so what this means is that the first principal component in this data set is latitude, and the second one is longitude. I think this is so amazing, because again, this PC thing is totally ad hoc. We're not using actual information about where these people are from when we're building them. We're just saying, oh yeah, like, what do our SNPs kind of explain? What's the maximum source of variation? And it turns out in our data, it's this geographic thing. Yeah?
Sorry, but I'm still not clear. How do you choose, like, because it's a principal, it's the first one, right? So how do you choose which SNP is going to be the first one?
So the principal components are eigenvectors of the genetic correlation matrix, of the relatedness matrix, I guess. And so each eigenvector has an associated eigenvalue. And so the first one is the one with the highest eigenvalue. But go ahead, sorry.
Sorry, yeah, but then I guess so when you do the, before you get to the eigenvector eigenvalue, so do you just use all of the SNPs
for
each person? Oh, okay.
Yeah, so you'll use all the SNPs, but yeah, so I mean the order shouldn't matter in terms of forming these principal components.
But then it's just so I guess what I was wondering is that it's so big, so do you need to use all of them, or do you know which ones to?
No, this is actually, you're right that this is actually kind of a big problem, right? Because the variance covariance, the relatedness matrix, if you have 100,000 people in your sample, is a 100,000 by 100,000 matrix, and getting the principal components of that is hard. There are a bunch of computational tools that have been developed to do this, and to do it actually pretty quickly. Yeah. Mm-hmm.
Just quickly, so what's the sum of the eigenvalues for PC1 and PC2?
Oh, I have no idea.
I'm just curious, because how much does the eigenvalue diminish as we increase the number of principal components?
That's a good question. I have no idea, though. Yeah, sorry.
This concept of a relatedness matrix is totally new to me. I mean, I guess I had thought that this was the variance covariance matrix of all the SNPs.
That's a relatedness matrix.
A PC out of that.
Yeah. When I say relatedness matrix, it's technically, I mean, it's closely related to the variance covariance matrix of the SNPs.
So, but you were variously describing it as how related each of the people is, which sounds different. So variance covariance matrix of the SNPs, I know exactly what that is.
But that's, well, so the issue is that, we have our data, right? So we have our genetic data, and this thing is, n by m, where this is the number of individuals, and this is the number of SNPs. And so we could calculate, xx prime, or we could calculate x prime x, right? And so this thing is going to give us, you hold the pair of individuals constant, and what's the covariance of all of their genotypes? And that's kind of related to this idea of relatedness. So if two people, if their genotypes covary highly, then that means they share a lot of the same SNPs, and so they're highly related. Whereas this matrix here is we're holding the pair of SNPs constant and talking about the covariance across individuals. And so if whenever you see a SNP in one location, you also see the SNP in this location across all individuals, then you have a high correlation in that sense, and that's LD. But they're related, just depends on kind of which thing you're doing here. And so when we're doing PCs, we're getting the eigenvalues of this variance covariance matrix.
So also tells you something about where people are from?
I mean, they're related, related things. I haven't thought hard enough about this to give you a but let's maybe chat about this later. I think this is probably not.
Okay.
Um,
Okay, I guess if you do it the other way, I guess I'm puzzled about how you go from the eigenvector that's about weights on people to what you need to control for PCs is some sort of eigenvector that's stated in terms of SNPs.
So I don't have an easy intuitive answer for it. I mean, like, connecting it to the technical things. I mean, I think that the intuitive answer is that these PCs are talking about, the dimension of the most variation. And so, the things that the SNPs are explaining the most of. And in general, that's going to be something related to ancestry. But I don't have anything less hand-wavy than that that I'll be able to answer easily. James? Yeah, which is.
It seems to you that we're getting the eigenvectors out of the wrong dimension matrix. Okay, yes, I thought about this once a long time ago. Like Patrick, I don't have an intuitive explanation. It turns out that these two eigen decompositions are related by this thing called the singular value decomposition.
Oh yeah, that's right.
And I have a book actually that explains this.
Okay, so there's some fun math that relates.
Yeah, it's like the eigenvectors for one is like the SNP loadings for the other or something. There's like some relationship like that. But
So I have a book and just one chapter of this explains this pretty well. I can just email it to you. Springer books, you can get it for free.
Great.
Yeah, that sounds great.
Why don't you put it in the Dropbox folder with the reading, so anyone who's interested could look
Okay,
at it.
all right.
Yeah, that'd be great. Yeah. Main point though is that these PCs are seem to be capturing important things about kind of where people are from and where their ancestry is from. So then we have some figures. So this is related. A lot of people have brought up this question of well, how many PCs? Like with our European sample, I showed you a picture, and the first two seem to be really good about getting latitude and longitude. But even within the UK, there's maybe stratification. So maybe one of the lower PCs captures that, but I don't know. We don't really know what these are, and so we might think, well, how many PCs do we need in order to get rid of these biases? And so this here is a regression coefficient from a GWAS of a SNP, and this is I think this SNP is on the gene that allows you to process lactose, on the lactase gene. And so we already know that there are different populations that are able to process lactose better than others, and so this is a signal that some of these people have this gene, this variant that allows you to process it, and some don't. And so this is the sort of candidate where we think there's major stratification. I think it's I think it's Asian populations, right, that they tend not to have the lactase gene. And so we might.
There's also a lot of variation within Europe. It's actually just hugely variable across groups,
Oh.
and it's commonly used as a kind of a test for kind of a case example for stratification.
Okay. So this is just a prime example of lots of variation in the allele frequency across different groups. And so if we just did a regression and we didn't control for anything, so we just have a big sample, we don't control for anything except for sex and age, then we get this enormous effect of this SNP on educational attainment. But then let's say it's okay, well, there's stratification. So I know that the problem with stratification is that there's these racial, ethnic, ancestry problems. And so I'm going to throw in just race as a control, and that's going to solve my problem. And so by doing that, you see a pretty substantial attenuation of the coefficient just by adding race. And so next you say, okay, well, maybe race isn't enough. Patrick told me that race isn't sufficient, and so let's add a PC just for funsies. And so when you add the first PC, so every additional one of these points is what happens as you add one more PC at a time. So one PC attenuates it a little bit, but it's still significant, and we still don't know that this is probably, it's still probably much larger than we think it should be. By the time you add the second one, we're no longer significant, and as we add more, it's wiggling until you get up to 8. And from this figure, after the 8th PC, it seems like we're kind of in a steady state here. Now, let's talk about this more in detail after I show you this one first. So let's say that, I told you at the beginning we should maybe just restrict to Europeans. That'll solve our problem, right? But if we do that, we still see the same sorts of issues. So in just Europeans, if you don't control for any PCs, just sex and age, we're still getting a pretty large coefficient within our European sample. One PC, it switches the sign, it's still down here, but it's still significant. And then as we add more, we're seeing that now it's just kind of hovering again around 0, and it holds steady after about the 8th PC. And so there's information being added about probably ancestry-related things up through here. And after this point, the additional PCs don't seem to be correlated with this particular SNP anymore. Yeah?
Do you have a sense of, so like the PCs, it seems like it can do two things. It could like remove spurious correlations, right? Because it's like we don't want those and they're on ancestry lines. And then if you took it to the limit and I just included like n-1 PCs, then I just have no betas, right? Like, or I have no meaningful information in my beta coefficients because it's all captured by the first n-1 axis of variation.
Mm-hmm.
Yeah,
so if you have, if you're confident that your SNP is accurately measured, so there's no noise, there's no genotyping error, adding additional PCs shouldn't affect, let me think for a moment. I'm going to make a claim that it shouldn't affect an expectation what's happening as long, once you've controlled for all the stratifications. Let's say that after the 10th PC, we know that we've gotten rid of everything. And if we add more PCs,
I was just thinking if I include all the PCs, I explain all the variations.
yeah, but this is a kind of a finite sample overfitting issue that you're raising, and not like an issue with bias or error or something. And so, in an infinite sample, the question is how many PCs could you add? And I think you could add a lot. But yeah, so over here it seems like once we get to 10, we're stable. This is going to be SNP specific though, right? So if the SNP let's say that the SNP is covariating due to, between a couple groups, and it's like PC7 that's capturing that type of variation, then yeah, you would get something like this. It might be that there's some SNP that varies across ancestry groups that's only explained by like PC10. I mean, I don't know that that's true, and I don't know that there's been careful work. I mean, you could do something like Miles was saying, where you could see how much variation due to stratification is left by adding more and more PCs. So that might be a way to try to get that. But as a general rule of thumb, I feel like if you just kind of add 10 or so, no one's going to complain. Yeah.
Sorry, I mean, if you sort of keep adding those PCs, I'm guessing the first set of SNPs or the first PCs will explain ancestry based on sort of SNP information. And then is there a danger that you get to a point when then what the PC is explaining is difference due to SNPs that contribute to the variable that you're interested in?
That's the question that I asked, not very well.
Yeah. So and there is the risk, but again, if your SNP is well genotyped, then adding additional PCs like that is a collinearity problem, which has big implications for power but not for bias. And so I think it's okay. Another thing to keep in mind is that we're calculating these PCs over a lot of SNPs. And so if there is one PC that's really highly correlated with a single SNP, there's something really funny about that SNP.
If it's highly polygenic, then you'd have a whole bunch of SNPs that contribute to a trait, and there is a possibility that they can, you might be able to get that.
Yeah. So again, I'm just trying to think sort of intuitively what would happen. I think you'd probably need to get much further than the 10th PC. If it's one of the first 10 PCs that is explaining a lot of the variation in one of the SNPs, then and again that SNP is really weird, because it means that if it's like one of the first 10, it means that we're first saying what's the first source of variation? What's going to explain most of the variation in all of my genetic data? And usually that's going to be some composite of a bunch of SNPs. Right? If the 10th PC is determined just by a single SNP, that SNP has to explain an enormous amount of variation in your genetic data. It just seems a little bit implausible. But I'm being hand wavy, and I acknowledge that. these PC things are a little bit hard. Again, they're kind of ad hoc. We use them because they work. 10 PCs is usually enough. I don't know if there's much more that I can say that's helpful.
Patrick, this is what you were saying a couple days ago about controlling what you said right now about bias, right? If you just add extra, covariates, it's not going to change your estimates. It's just going to change your standard errors, right? For regressions.
Yeah, for something like this.
Collinear.
Mm-hmm. Oh yeah, I mean, to the degree that it's collinear, yeah, it can make your standard errors very big. If there is genotyping error, it can cause problems, but if you feel like you have a cleanly genotyped SNP, then you should be fine, especially up through the first several PCs, I'd think.
I mean, here too, I think it's an example where the medical genetics community was scarred by having these non-replicable results, and so is willing to be, to err on the conservative side, and just isn't that worried about, controlling for PCs that'll increase standard errors on the SNPs, because we want to make sure that whatever we're getting is real.
Mm-hmm.
Sorry, tied to that, you also have I'm guessing, PCs can also control for batch effects if you're doing.
Oh yeah, that's important as well.
So
Mm-hmm.
tied to that, do you have an idea of I guess it's a very sort of vague question, which PCs would control for ancestry, and beyond that, which PCs? I'm guessing ancestries would be the first major source of variation.
It depends on how big your batch effects are. Right? I mean, if there was this, you could have some weird batch effect where just on average it boosts the, if in this one batch all of your allele frequencies go up by 10%, just due to some weird error, and in that case the batch effect's going to be the very first one. But yeah, and again, this is the hard thing about these PCs, is we don't know what they are. We just know that they tend to work. And just to highlight the point he said again, just in case you didn't hear. So we've been talking about these PCs in terms of just ancestry. But let's say that you gathered your data in kind of two waves, and you sent half of your data to one place, and you sent half of your data to another place. And let's say you sent all of your men to one place and all of your women to another place. Then because of these batch effects, there might be just kind of subtle differences in the errors that are introduced into your genotypes. And so as a result, your genotype's going to predict which batch you came from. And if the batch you came from is correlated with your phenotype, then you'll get these biases again in the exact same way that we saw before. And so, so the PCs should also capture this, though, if the type of error, so if these errors are big enough that the first few PCs can get it, then it should be able to capture that as well. Although Fleur was saying that they had examples where they were observing batch effects in their data that the first several PCs, it didn't look like it was catching it, and so they just had to throw the data out. Or they had to I don't know if they actually threw it out, but they said it was really bad because of these batch effects that happened to be correlated with their outcome.
Can you not just include batch as a variable in the regression?
Yeah, so you could do that. Mm-hmm. And I think that's what she said they did, but for some reason she was worried about that too. I mean, it might be that if you see these batch effects, then you're just kind of worried in general, and you don't know, you see that something's wrong, and so you don't know what else is wrong, right?
The UK Biobank has instructions about what you need to do when you analyze their data, and it includes, put in certain controls for batch effects, which they know are in their data.
Okay, so I just want to talk. This is a kind of technical point, but I think it's a nice thing to understand for why PCs work. And so this is our favorite theorem, the Frisch-Vaug theorem. And so this is going to help us understand about why PCs might work. So let's say that we're going to be super general. Let's say that we want to estimate this regression. So in this case, it could be this could be a SNP, and this could be one of these fixed effects, ancestry fixed effects, and this is our phenotype. But we want to estimate this whole model, and we want to. But I don't want to do a multiple regression. I only want to do simple regressions because those are my favorite. And so what you can do, so equivalent to actually running the multivariate model, to actually running this regression of the phenotype on both of these things, we could do this procedure. So first, we could regress A on just B. So we're doing a simple regression of A on B, and then we can take the residuals of that. Or A on C, because we're going to actually omit this guy. So we're going to regress A on C and take the residual of that. So now we have A tilde, which is the residual from that regression. And then I'm going to regress B on C and take the residual from that. And so now we have B tilde. And then I'm going to regress the residual of A onto the residual of B. If we do this like simple process of a bunch of simple regressions, this will give us exactly the same coefficient. Like it's not even like an expectation or an approximation. If you do this exact thing I told you, it's going to get you the exact same estimate here as you would get if you ran the whole regression with both variables in it at once. So that's Frisch-Vaug. And this is going to be really helpful for us to understand why PCs might work. Okay? So if we think that our C is ancestry or some proxy, so in this case like our principal components. Okay? So first, when we regress out, when we regress the phenotype on our principal components and then take the residual out, that's essentially removing the variation in the phenotype. So let's write this down on the board because I think that you can't. I'm talking, and it'd be easier if you could see the equation as we're talking. So our model was this. Y is equal to x beta plus g, right? So in the first regression, where I regress y on just g and take the residual, all that's left in y is variation that's not due to g. We've removed so all that's left is things that are uncorrelated, correlated with this g thing here. So y tilde doesn't contain any information about these ancestry fixed effects. Right? Same thing when we regress the genotype on g. What we have left when we're done there are SNPs that don't contain any information about a person's ancestry. Right? So when we have x tilde, these are kind of ancestry-free genotypes. And so now when we regress this onto this, now if you recall, the sources of bias due to stratification there were two things. It was correlation of the x's with the g, but this x tilde, by construction, is not correlated with g. And so those biases are going away. And there's also correlation between the x's. And if we've regressed each of the x's on g, then all of those things are uncorrelated with ancestry. And so they're, if before they were correlated with each other because of ancestry, they're not going to be correlated in that way anymore. And so removing the variation that was creating all of these biases by adding these principal components in. And so that's sort of a kind of a technical way of, to help you kind of understand when we say we're controlling, what does that mean? How does that work? And I think that this is sort of a helpful thing. When we say we're controlling, it's because we're removing the variation that is predicted by the controls from both the phenotype and the genotype. Okay? So it's so something that we often do due to computational reasons is, we're running like a ton of regressions, right? And so simple regressions are very easy to run. Whereas multivariate regressions, you have to invert that matrix, and so that's maybe hard to do. Like each individual one is not very hard to do, but you multiply that by 10 million, and that's a little bit hard to do. And so to save time, sometimes what we do is we just kind of do one step of this. So we'll regress the phenotype on, instead of G, I'll replace this with our PCs or other controls like sex and age. So we'll regress out all these controls first, and then we regress the residual onto these genotypes. But what we don't do is we don't residualize out the X, because that's hard. The X's are really easy to store because they're just either 0, 1, or 2, and so it's really efficient to store them that way. And if we residualize them, we'd all of a sudden have to store them as like floats. And so that's going to be hard to do too. And so just for computational reasons, we'll often do this. And I think that's probably what are they doing this in the problem set? They did last year. Robbie? Yeah, so in the problem set, you're going to do this too. What you should keep in mind, though, that this is not equivalent, because we've not removed ancestry from the genotypes when we do this, and so there might be kind of subtle sorts of problems due to that reason. Yeah.
So I was trying to ask earlier. Let me see if I can put it better. So let's say there's like a true causal relationship between a set of SNPs and, let's say, Y is educational attainment. Why is it not possible for one of your PCs to be that linear combination of SNPs that's exactly what you're looking for? And if you control for it, then you lose what you're looking for.
So I wouldn't say that it is impossible, but it seems unlikely. You would need for the kind of weights associated with each of the SNPs to be exactly equal to the weights that give you your, our true causal weights from kind of our model. And that could happen, but we're not using genotypes, or we're not using phenotypes to make the PCs, so it would just be pure coincidence if that happened.
I mean, this is something you can test empirically if you want in R and see what happens when you include it. You can do like the variance inflation factor or whatever and see what happens. If you think that for some reason some P is highly correlated with your trait or whatever, then try it.
Mm-hmm. Yeah, as a general rule, I get really nervous about kind of the try it and see what happens mentality. But I do agree. If you have a strong reason to believe that it's a problem, and so you have a specific hypothesis that that this PC is actually causing all of your problems in life, then yeah, sure. But be careful and once you start just kind of trying things out, you're really at risk of kind of inadvertently doing kind of p-hacking sorts of things, right?
I think there's an example that might make this clear. So suppose you want to look at things that predict lactose intolerance, and so you control for these PCs, but presumably there's some variation in these lactose intolerance genes, even within East Asian populations, and some variation within the Western populations. And if it were really okay, this gene only exists in this population, and it's gone to 100% and is 0% in this population, then the only data you have is comparing the populations anyway, and you would have looked at that long before and deduced whatever you could possibly deduce from that long before you ever did the gene data. But unless both are fixed, one at 0 and one at 100% in both the populations, you're going to have evidence, and it's only a power issue.
Yeah. Mm-hmm. Yeah, that's a good way of describing it. Mm-hmm. But the power issue could be, I think people are worried that this power issue is going to be substantial. They what?
In practice, we don't think it is.
Yeah, exactly. And so in theory, it could be, but just based on the experience that we've seen with reasonable phenotypes, it just doesn't seem like it is.
So if you residualize a typical SNP on the first 10 PCs, the variance in the SNP is basically unchanged to first approximation.
Because I think I asked Robbie, I think that the variance explained by the first 10 PCs or so is like 4 or 5%. Yeah. Okay. Okay, so one last thing to kind of give you a connection to another thing that you can kind of do, which is related. So when we add the PCs, we can kind of think of those PCs as a predictor. Like our PCs are a polygenic score of some sort that are predictive of a person's ancestry because they include these additional SNPs that are predicting a person's ancestry. And so if we want to think about these PCs as a predictor that is contaminated by ancestry, we could, why use PCs to create a predictor? We could actually just use all the SNPs to predict the outcome using something like ridge regression or lasso or any complicated whatever we want to use. And that predictor is going to be contaminated by stratification. It's going to be, we don't like that. However, it's going to be contaminated by stratification in the same way that the phenotype is. And so we could then subtract out that predictor from the phenotype and hope that this removes all of the variation due to these ancestry things, because all of that variation was living in the predictor we made before with all of the SNPs. And so, so a procedure kind of like that is what people in the genetics literature often call mixed linear models. And so this is different than what we call mixed linear models in economics. I don't know about other fields if they call mixed linear models something else. But there's something to keep in mind. When you see mixed linear models in different contexts, it can mean slightly different things. But in genetics papers, if they say that they've run a mixed linear model, they've done something that's a variation of the thing I described. They're essentially predicting, they take all of the SNPs and they predict the phenotype, and they understand that that prediction contains all of these stratification biases and problems. And so they subtract that out of the phenotype and say, okay, we've removed, these both had the stratification. We subtracted out, so we removed the stratification. And then they regress the residual from the prediction analysis onto the SNP. And so this also seems to work pretty well at removing stratification. But there's what was this point I was trying to make here? Sorry. The problem with this is that is kind of related to these issues that other people are bringing up. Let's say that the SNP is being, this predictor that we have, we're removing variation from Y that's due to this stuff here, but we're not removing variation in X. But let's say the predictor is predicting X, and so instead we're running this model, which is what you're going to do in your problem set. This has all of the variation due to ancestry taken out. This has additional variation due to ancestry that's still in it. And so this is going to cause some bias because there's additional variation here that's not going to be relevant to the variation in this because we've removed it. And so this will attenuate our estimates. But it won't do it very much. And so we don't tend to worry about it very much. And this seems to be really effective. And there's really fast methods that have been developed that can do this. But when you see it, you can think of it as it's a variation on this PC thing. They're creating a predictor, and they're differencing it out of the phenotype in order to remove the differences in levels that exist that are causing us headaches because our population is stratified.
Maybe I'm confused, but how are you getting around the rank order condition in that case?
So when you're doing prediction models like Lasso and Ridge, there is no rank order condition that you need to meet. That's kind of one of the your betas are not interpretable, okay. But you can create a predictor even without the rank condition. Okay. Yeah.
Maybe I'm understanding this wrongly, but are you saying that using this method, we're essentially taking out the last part of the stratification bias, but we might be still having the stratification bias like the first term?
Yeah. So this is maybe one way to look at it. So we have y is equal to like x1 beta 1 plus the sum over j equals 2 to m of xj beta j plus g, plus the error, right? So when we do a GWAS and we want to estimate the effect of this thing here, and so we predict using these SNPs. And if we wanted to be careful, we'd probably just choose the SNPs that are on like other chromosomes to avoid LD problems. So let's say, well, I don't want to write that. But yeah, so we'll predict using this. This thing is going to be highly correlated with the problematic parts of G. So the parts of G that are correlated with ancestry, and our SNPs are correlated with ancestry. And so when we create a predictor based on this thing here, it's going to absorb the annoying variation that lives here, just because they're correlated, and so our predictor is going to pick it up. And so then once we're going to subtract, so we'll call this kind of like y, y hat. Right? And so then when we say, y minus y hat, all we're left with is this piece. assuming that we got, plus some error.
So is this sort of jackknifey where we're taking out the x1 beta 1 from the rest of that each time, and then for the x2 beta 2 we'll put x1 beta 1 back in?
Yeah, I mean they usually do it chromosome at a time. And so yeah, so this they'll predict based on everything that's on a different chromosome.
This definitely looks inferior to doing the PCs because it's a little bit like doing one weird PC.
Well, this should capture. So like the one PC may not capture all of the dimensions of.
This is a one-dimensional thing.
But it's a one-dimensional thing that we've estimated by estimating a lot of parameters. And so the idea is we've collapsed. So so you could think of PCs as a version of this, right? Like this y bar could be equal to a weighted sum of the betas, right? Or y bar could be equal to, and I'm running out of letters, gamma. A weighted sum of the PCs. And hopefully these contain the same information if you've done your prediction correctly. Right, so if you just do one PC, then this is really just kind of one dimension, and it's a dimension that's not at all, you're not tuning the PC to help you be predictive of the phenotype. Whereas the weights of our predictor in this model are chosen specifically to absorb the variation that's related to the variation in here, which includes ancestry.
It's based on a kind of unrelated variance, and then this is based on the covariance of interest itself.
Mm-hmm.
And so there's still some assumption about how kind of the amount of bias you're getting being similar across chromosomes. That kind of whatever the stratification is, you can kind of detect the stratification issue
from the set of SNPs on that chromosome. But if we think that the reason that we're correlated with these fixed effects is because of random drift, then every SNP contains a little bit of information about ancestry. And so we should be kind of capturing the same kind of variation no matter which chromosome we hold out.
Do they ever try to do this with non-coding genes, or is there just too much LD to focus in on non-coding genes?
I've never seen that done. It seems like LD is going to be a problem. But it should be fine as long as the SNPs that you're using to create this predictor are uncorrelated with this one because they're on a different chromosome. Then it should be okay. And in fact, you maybe want things that are highly predictive and highly causal because by removing the variation from here, you're removing residual variation, and so you're getting more accurate predictors. And so these type of methods not only potentially remove stratification, but they also increase precision.
So now I kind of gather that you mostly not used this method. Is there a reason that you've leaned away from this method?
This is becoming actually quite common, especially when you have related samples. And so like in the UKB, I think our default is using this these days because a model like this may allow you to correct for like siblings that may exist in your sample.
So Patrick, we should wrap up, but just one quick thing I want you to answer.
Mm-hmm.
In practice, you talked about methods for correcting for stratification. Correcting the coefficients and correcting the standard errors. In practice, which do you do?
I mean, I think we do both, right? So we're gonna try to throw everything at it that we can. And so like first thing, we'll do things like this, and then we say that well, hopefully this gets rid of the stratification. And then we can do things like LD score regression, which allows us to correct our intercept. And even before we do the correction, we can actually assess how much stratification is left after we do something like this. And doing these kinds of things after we do LD score regression, it tends to, it looks like there's not really anything left.
Okay, so I think we should take a break now for 10 minutes, and then